No, okay, let's start our lecture. Let's finish our general observation about Koszul resolutions. Now we proved last time that if I have commutative ring and I consider some regular sequence such that no fi is not zero divisor in quotient of the previous f1 fi minus 1. Now then I have Koszul resolution of such ring over R. It's Koszul resolution of the something like this over R. Yes, with Koszul differential. It's free acyclic resolution. No, it's free resolution. Koszul resolution. No, sorry, it's no, yes, it's true. Yes, Koszul resolution of this ring over R. For example, was the important example. It's general. It's a general resolution. No, but simplest example where when your R is polynomial ring and you consider these variables as a regular sequence, then you obtain quotient is k itself, and you obtain free polynomial resolution of k itself. It's of this form. We can consider this as big-graded algebra. Where here is even degrees, here is odd degrees, and you have Koszul differential, which satisfies Leibniz rule and sends ui to xi. And also, yes, no, and for example, from this, yes, and you from the definition of, for example, you can check that. No, you see that image of this differential lies in positive degree, so in fact this resolution is minimal. If you tensor with k, you obtain zeros. It's minimal resolution. No, if you tensor with k, you kill off all positive degrees in xi, and you see that from the definition that image always lies in positive degree. So if you tensor with k, you obtain that all differentials are zero.
Question. The image of this difference is not in our field. How we?
It's differential in this big-graded algebra. No, and satisfy Leibniz rule if you want. You have some wedge form, you have some polynomial, and from this, and of course, and xi goes to zero. So from this is generators of your algebra, and so by Leibniz rule you can obtain what the image of D on any element. No, this one is the last one. It's where you have no wedge form, only a polynomial itself, and then this map goes xi to 0 and unity to unit. So it's the last differential. On this differential is this form. Okay, this is minimal resolution. So in fact, we obtain that Tor I over polynomials of k and k. This is resolution for k, and if I tensor with k, I obtain this minimal resolution for k, and so I obtain this is just dimensions of these things. So this is dimension. This is as vector space over k is just ith graded component of extrareal algebra. And so we obtain that in particular, we know dimensions, and in particular we see that this resolution is has finite length, and we know that length of minimal resolution is minimal length, it's projective dimension, so we obtain that projective dimension of k over polynomials is exactly n. It's exactly the length of this Koszul resolution. And from this we can say that Hilbert CZ, I don't know how it, I don't know. CZG theorem that in fact global dimension of polynomial ring is n. So in fact, projective dimension of any module not greater than n. No, and n is exactly for k. No, sorry, it's for k is exactly n. No, in our assumptions, you can prove this in grading sense. No, in grading sense, it's more or less obvious because no, okay, I need to. We know that from this thing, projective dimension over some graded ring of M is maximal where Tor I over our ring A mk is not 0. Yes. No, because it falls from minimal resolution for M. No, okay. So we need to check that for any model of polynomials, these things n plus 1, for example, is 0. But sorry. Maybe it's not true. Yes. No, in opposite direction. Yes. Projective dimension is it's minimal where it's 0. No. No. Sorry. It was true. Maximal not 0. Yes. Okay. And no, because it's just minimal resolutions. It's minimal resolutions for M tensor K. It's 0 if and only if it's 0. Okay, and so, but if we have any module M or polynomial, to compute this Tor, we can use minimal resolution for K because we know that Tor is symmetric. So, and if we use, and we know that we have minimal resolution for K of length n. So we obtain that if we have minimal resolution, Koszul resolution for K, then tensor it with M and compute homology, we obtain that this is 0 for E more than n because it has length for K. It's homology of Koszul resolution of this thing. Tensor M. This complex has length n, so it's 0 more than n. So we obtain that projective dimension less than n. And it's n, for example, for k. So we obtain this observation. For example, okay. In general, it's important here that k is filled. In general, global dimension of polynomials over some ring is global dimension of this ring itself plus n. Okay. Yes, and also I say that we have how we can. Of course, we know that in general, Koszul complex is general acyclic complex for any regular sequence. But I said that in this situation, for example, we have the RAM differential, and we have that this equality. This is k plus ID on this quotient, on this graded component. So up to normalization, D is chain homotopy between Koszul differential and 0. So if characteristic of k is 0, I can divide by some elements. I have to do this normalization, and I obtain that D is homotopic. Koszul resolution with Koszul differential contractible. It's an exercise that in fact it's contractible for any ring. It's also not very hard observation, but vice versa. Of course, from this I can see that in this assumption also this complex with the RAM differential also contractible because Koszul resolution is homotopy between differential DRAM and recalling the RAM differential is the opposite one. It goes xi to ui and ui to 0. From this one is also contractible. And so this means that we can consider this, the same big-rate algebra as a free resolution of K over X real algebra, yes? Because it's acyclic, because it's contractible with d differential. So this thing with the RAM differential is, if characteristic is 0, then this is a free exterior algebra resolution of K. And we and from this, and it's also minimal by this equality again. And so we obtain that we know Tor. No, and X, yes, I didn't say that, but of course we know Tor and X. We know, again, we know Tor over polynomials from K to K is exterior algebra. Here it's vector, yes, okay, it's some variables, not. No, and X also, we know that X from K to K. Yes, it's also the same thing. And dually, it's true for any K. And for in characteristic 0, we obtain that Tor over exterior algebra from K to K is polynomial algebra. No, in particular, we see that it has infinite projective dimension. K over exterior algebra. No, and X, the same thing. But this is, in general, this is not true for not characteristic 0 K. In general characteristic, you obtain not polynomial, you need to use, as we see before, something like divided powers algebras. You need to consider the general divided power algebras, gamma, in some variables. And this is, and you can define some differentials here, and this is also, it's called the Koszul resolution, but for exterior algebra. So it works for any field. No, maybe we will discuss it later, maybe. No, what I want to say that this is not true for not characteristic K0. In general, characteristic is not polynomial algebra, it's kind of divided power algebra. As we see for it's a homology of loops of sphere. In general, it's divided algebra, it's divided algebra is a modified polynomial algebra in characteristic 0. Okay. Now we see, for example, for characteristic 0, we have something like this. No, at least it's infinite dimensional, for example. Okay. And now I want to give a final remark about some some generalization of this situation. Maybe, of course, general Koszul resolution is general thing. It's for any regular sequence. But we have generalization in some other direction. For example, let's consider the following situation. Let me have A is finally generated associative graded associative algebra. Graded associative algebra, with unit. Maybe not commutative. This means that it's, what does it mean? This means that I have some, graded and finally generated, for simplicity, for example, okay. I have some vector space, for example, graded vector space generated by generators. It's a vector space of K. And I have tensor product, tensor algebra, it's free associative algebra of these generators. And I have a subjective to my algebra. This means that it's finally generated graded associative algebra with unit, okay? For any, for example, graded vector space, or if you don't like graded, then you can assume that A generated by elements of the same degree, and you can say that it's not graded vector space. You have tensor product. It's free associative algebra. If all tensors, I have all tensors, I have associative property, but I have no commutative. It's free associative algebra. No, for example, if I have T of Kn, it's the same thing as T in n letters. No, because linearity is also in tensor product inside of the tensor product definition. So I have, of course, if I know how to multiply letters freely, I know how to multiply all linear combinations of letters by linearity. Okay. So in fact,
Algebra free, but not community.
yeah, yes, it's free associative algebra, and so
I mean tensor algebra.
yes, of course, it's tensor algebra. It's not commutative in general. No, it's commutative if it's generated by one dimensional. It's only yes. So I have this surjection. It's kind of generators, and I have ideal of relations. It's some graded ideal, so on. We say that algebra is quadratic. No, yes, and what is the relations here? No, yes, it's A is quadratic. Quadratic algebra, quadratic algebra. No, if I lies in V tensor V. So all relations are quadratic relations. Then, for quadratic algebra, you can define dual quadratic algebra. Dual quadratic algebra, something like this. You need to consider associative algebra on dual vector space. If you have such inclusion, then in this thing you have what you have. You have annulator of I, yes? Something like this. I think yes. No, yes, because you have with respect to the natural pairing between V and V star. Yes. No, this is, and under the natural pairing between V and V dual, you have annulator of some vector subspace. Yes. No, and this is modular this thing. It's also quadratic. It's some ideal. It's also quadratic ideal. Sorry. No, of course, ideal cannot be quadratic. I mean that ideal is generated by quadratic. Ideal E is ideal generated by the by its quadratic part. Okay. No, of course, if you have quadratic relations, you also have quartic relation. It's square of quadratic relations. It's not quadratic, but it's generated by quadratic relations. Okay, yes, sorry. No, so yes, you have this, this thing, yes, quadratic part, and this is, в общем, yes, generated by this quadratic part. It's also quadratic ideal, and so you have dual algebra. No, for example, what exercise? Check that. What the quadratic, first of all, quadratic dual or quadratic dual, what is it?
Maybe 8.
No, yes, it's called dual not just for fun. Yes, it's duality. It's algebra itself. Then, if you consider, for example, free commutative algebra, what the dual of free commutative algebra? Commutative algebra, it's quadratic algebra. You can check that it's quadratic algebra. And what the dual? No, it's extrareal algebra. No, and vice versa by the previous one. You can check this. No, and for example, you can check what the dual of the free algebra. It's question. It's exercise of question. Okay. It's for example, and so this is generalization of our previous example, and in fact we have Koszul complex in this situation.
In the definition we have stars.
No stars, yes, no, but if you choose basis, then it's the same dimension vector space. No, yes. No here, no, yes, because from geometric points of view, this is kind of dxi, it's kind of linear functions on this affine space. Yes, it's kind of dual. But they have the same dimension. So this is because the other letters. Because this is, in fact, linear forms, linear functions on xi. No, they have the same dimension. Yes. No, isomorphic. No, if you want. Okay? As algebra is isomorphic to extra algebra in the same number of generators. Okay. No, maybe. No, yes. Maybe you don't need grading here. No. Yes. Maybe you can ignore grading here. It's not important here. What's Koszul element? Maybe you know what's Casimir element in the algebra theory. No, it's kind of the same thing. Oh.
I only know what is function Casimir.
No, Casimir function. No, it's more or less yes. No, I want to define. Yes, I want to define Casimir element. Casimir element. No, it's just if I have algebra and dual algebra. No, yes, no, because no, in fact, you have kind of duality between them. You have duality between them. No, because it's tensor algebra generated by dual space and modular annihilator of your relation. So in fact, you have duality between the two algebras, and so as always, if you have duality, you can consider, no, for example, a dual. No, okay, for example, in coordinates, you have basis, no, generators, basis of your v here, and dual basis here. Now then, Casimir element is something like this, as always. Now, with respect to duality, it respects to the identity element. If you consider v, for example, tensor v star, you have this element corresponds to identity operator. Yes. Oi. It's Casimir element, and no, then you can consider action of this element on such thing. You can consider a tensor a dual and linearly dual. What do you think? Well, then you can consider multiplication by k. No, what's multiplication? No, it's just no. Always, if you have if you have some element a tensor, I don't know, alpha, it's from a, it's from a dual. It's kind of our Casimir element. It's sum of such elements. And if you have element from this thing, it's, I don't know, b tensor phi. Phi is functional on dual algebra. Now then, of course, you can multiply them. If you multiply, you obtain. No, in fact, I think that it's more or less clear how Casimir element acts, or it's not clear. Now, how can I? No, it's something like no, okay. In this situation, it's something like a tensor alpha x on b tensor phi. It's kind of a b tensor phi alpha multiply something. It's new functional because it's algebra, and I use multiplication here and here, and pairing. No, it's a natural action of this thing on this thing by multiplication here and by I don't know, you action via multiplication on the functionals here, and so I have action of Casimir. No, in these terms is kind of Casimir of a tensor phi is sum of E tensor там phi EI там something like this.
Where does this element
Huh?
AB tensor phi?
No, it's element from this again. It's functional on dual algebra, and this is element from algebra. It's X on this.
Can I ask?
Uh-huh.
Alpha is a linear function on
Yeah, alpha is element from dual algebra. I have two algebras. No, it's not here. It's not important that it's dual. It's just elements from. No, if you have two algebras, then then you can act by tensor product these two algebras on algebra and the dual of algebras, for example.
I just don't understand what's mean phi bracket open alpha.
No, it's new functional because alpha is from a dual. This is a functional a dual. If you have algebra and element phi from B is algebra, then you can consider it's B multiplication by B and then functional. And this is again from this thing. Okay?
So phi is not element of dual algebra. It's something.
No, phi is from here. This element is from here. It's dual it's dual to dual algebra. It's functional on dual algebra, and B is from A. Yes. Because I want to act on this thing by to these algebras. No, okay, and you can check. Then the first one that Koszul squared is 0. So the section squared is 0. So this is chain complex. Chain complex of what? Now, if I have K is field, then this is vector space, and this is free A modules, for example. So this is chain complex of free A modules. No, and if you consider, for example, if you have unit, and if you assume that your algebras are connected, in graded 0 you have only unit, so the last grading of this algebra is just K, and so last grade of this complex is just A, and if you consider augmentation to K, you obtain Koszul complex. Koszul complex is what? Something like A, K, then what's the time? First grade component and so on. It's Koszul. It's Koszul complex of quadratic algebra A. You can check that if your quadratic algebra is polynomial or external algebra, then up to normalization then this Koszul differential is up to normalization is Koszul differential, maybe divided by m on lambda m tensor k. Something maybe in graded m you need multiply or divided by m, something like this. So this is generalization. And but for polynomial algebra it's exact complex, it's acyclic. In general it's not acyclic. And algebra called Koszul algebra if this thing is acyclic. So A is Koszul. By definition, if Koszul complex is acyclic. It's equivalent that for dual algebra it's cocyclic, because for dual algebra it's kind of dual complex.
We multiply A by first degree elements in A dual.
You can check that this K increase degree in A by increase degree in A by 1 and decrease degree in A dual by 1 also. So in fact it has something like this form, yes. From A1 to A0. A0 of this thing is K, so it's just K here. And so on, yes. In fact K acts from N M to to n minus 1 m plus 1. But if I consider all a, so I have here I have decreasing of gradient, yes. Because of this definition. Okay, and for example, this algebra is Koszul algebras. You can check that free associative algebra is also Koszul algebra. So for such good algebras, you can and also you can check in fact that under some mild assumptions that in fact these resolutions are minimal. It's also minimal resolutions. In fact, if it's Koszul, then it's minimal resolution, and so you can obtain some construction of minimal resolution in this situation for quadratic algebra, which when it's acyclic, then it's minimal resolution. Also you can some properties when it's acyclic. For example, if you consider this dual algebra and consider opposite algebra, it's the same algebra with the opposite multiplication. Then it's isomorphic, in fact, to Untitled algebra of x from k to k. And it's Koszul if and only if this algebra generated by elements of the degree 1. It's some homological criteria of Koszulity. In fact, you need to check Koszulity in general, but in some situations you have Koszul resolutions. And why I really wanted to say about this, because in general, consider, for example, universal available algebra of Lie algebra. If you have Lie algebra, you can consider universal available algebra. What is it?
Universal can be
If Lie is Lie algebra, what is the universal available algebra? Yes. What is it? It's associative Lie algebra. It's associative algebra generated by the same vector space by the relations that the commutator in algebra is the same thing as the commutator in Lie algebra. This relation is not quadratic because it has a linear part. But you can mildly generalize this picture to quadratic linear algebra. If your relation is generated by linear and quadratic, in fact, you can forget linear parts. It's so-called quadratic reduction of this algebra. And then you obtain quadratic algebra, and you can say Koszul, not Koszul, consider some Koszul resolution, and in fact, in some situation, it will be a resolution for the original algebra. For example, what we obtain if I forget this linear part? If I symmetrize this thing. It's symmetric algebra of G, it's polynomial algebra. In this situation, it's always it's so-called it's Poincaré-Bergov theorem. It's the algebra of it's graded quotient algebra. If you consider filtration on this algebra, yes, by monomials, then it's filtration multiplicative, and if you consider graded quotients, you obtain exactly polynomial algebra. It's kind of Poincaré-Bergov theorem. And it's a general situation if you have quadratic linear algebra and you consider this reduction, and this thing is the graded quotient of the filtration. And what I want to say now that this algebra is polynomial, is Koszul. And if you consider Koszul resolution for this, you obtain so-called Chevalier-Hillenberg resolution for universal available algebra. It's associative algebra. For example, you have bar resolution here, but also you have Chevalier-Hillenberg resolution. It's kind of Koszul resolution. It looks like Koszul resolution. It consists of extra algebra and so on. And this is not coincidence. It's because it's quadratic linear algebra, and this reduction is Koszul. So you have Koszul resolution, and from this, of course, I hope we will discuss it later, maybe in beginning of December. But maybe we will not discuss in the context of Koszul resolution. But we will see that, in fact, in this situation we have Chevalier-Hillenberg resolution. Chevalier-Hillenberg resolution. It's not very obvious because to check that this resolution, maybe we will use some spectral sequences. But in general, it's kind of part of the general context of quadratic linear algebras and Koszul dual algebras and so on. It's what I wanted to check. No, in quadratic context you can check this directly. In quadratic linear you need some more checkings. Okay, that was what I wanted to say about Koszul resolutions. Now let's say something about regular sequences in modules and in rings in our graded situation. Yes. Значит, I recall that I have A is commutative, evenly graded, non-positive, non-negatively graded, connected key algebra. Then elements of ordered sequence of homogeneous positively graded elements, homogeneous positively graded, is called regular if xi is not zero divisor in quotient modulo the previous one for each I. Okay, what we can say in this situation? First of all is exercise. No, because it's really very direct check, very direct calculation by definition. You can check the following: that if you have exact sequence of A modules, for example, short exact sequence. No, it's not important. Okay, if you have exact sequence of modules, exact in this place, over A, then if you consider quotient modulo this sequence, modulo ideal generated by this sequence.
We consider modules by over A.
Over A, yes, it's graded. All our modules are also graded, non-negative graded.
Is A.
Yes. No, this is, yes, this may be, okay, this is sequence, but also this is ideal generated by these elements, yes? And for any model, I can consider a quotient by some ideal, okay? And this is module over R modulo I. Yes, and maybe let me denote such ideal by something like this, no, for simplicity, okay? Then this sequence also exact over quotient ring. Exact over A modulo X. No, this is direct calculation. It's by definition, not something interesting here. No, but
By C quotient ideal generated by X.
Yes, значит, I always will denote X is this ideal, yes.
But C we have X.
If you have some module over R and you have some ideal over R, no, then okay, in this situation, by this I denote something by this. It's a submodule. Yes, and by this I will denote quotient by submodule, of course. Так, okay. Okay. From this we can obtain some interesting corollary. No, for example, okay, let's we see the first easy criterion of regularity. Regular. Yes, maybe. Sorry. Let me a little bit extend my definition. This sequence of elements in A is regular in M. Yes, if xi is not zero divisor in this quotient again. No, because this definition makes sense for any module. Okay. Elements in ring, but they can be or not, or can be not regular in some module. And then this sequence is regular in M, But we assume here that they are homogeneous and positive degree. That's important, in fact. It's our graded situation. The regular if and only if m. No, again, I have such elements. I can multiply any element in M by xi, for example, yes? I can multiply any element M by xn. So in fact, M is the module of a polynomial algebra. Okay? No, in this notation, I mean that I multiply any variable in M as element in A, okay? Maybe I can redenote it if you want, but I think it's more clear if I, okay? It's not subalgebra in A generated by these elements. Maybe it's not polynomial. I have abstract polynomial ring, but I have action of this ring on M if I have n elements of my ring, okay? No, if you wish, I have some map to A, and then I act on M by this map, okay? By this ring homomorphism. No, so this sequence is regular in M. If and only if this model is free model of this, is can free. It's free over such polynomial. No, upstairs is obvious, yes, because it's, if it's free, then all this. If you consider quotient, if it's free, then quotient by previous one it's free over remaining variables, and multiplication by element is non-zero divisor because it's free module in polynomial ring. Okay, it's by definition. So from this to this, it's more or less obvious. No, it's corollary because of that one xn is regular in polynomial ring. Okay, it's clear that from down to up. No, from up to down. No, okay. Ой. Так, from up to down we need one observation. Okay. Yes, I have regular sequence. Then M, no, as I said before, is k x1 xn module. I need to check that it's free module. Now I can consider free minimal free resolution. Minimal free resolution of a polynomial of this polynomial ring over polynomial ring. And then I can consider quotient of this resolution modulo x1 xn. On the one hand, I obtain, no, it's the same thing as tensor over polynomials with k. So we know by definition of minimality, I obtain that all differentials are zero except of this. All differentials in the resolution became zero. Okay. Because of minimality, all differentials are zero. No, except of the last one. But on the other side, from this exercise, I obtain that it will be exact because it's quotient by regular sequence. So it's exact and with zero differentials. No, which this means that all my terms in free resolution are zero except of the last one. So in fact, and from exercise, it's exact. And so I obtain that all minimal things are zero except of the last one. So I obtain that M is isomorphic to F minimal. So it's free. Okay. No, it's important that this is exercise, but this exercise is directly checking. Okay. And from we know that I have minimal resolutions. Fun corollary from this is that that property of ordered sequence to be regular does not depend on order. It's a property of unordered set of elements, because this property does not depend on order. If I have permutation of variables, it's some automorphism of my ring, and if my model is free over this polynomial, this is also free over permutated ring. So in fact, we obtain corollary, it's important corollary, that regularity does not depend on order. No, it's not true in general, but in our assumption that it's homogeneous elements of positive degree in graded situation, it's true. It's also true in local situation. No, it's something like this. It's not general. In general, it's not true. Maybe in some weird situations. Okay. Now I want to check something about how many regular elements you can have in your ring. You can say I want to say something about this. So for example, what if I have regular sequence or regular set is called maximal. No, if it's maximal with respect to inclusion. If I cannot extend it to a regular sequence of with one or more element, okay? No, it's equivalent to say that in the quotient any positive degree element is zero divisor. And theorem of Rees say that number of elements of regular sequence is called length of regular sequence. Call that length of any maximal regular sequence is the same. It's called depth of module. It's called depth of your module of your ring, and it's equal to minimal I such that x I over a from k to m is not zero. So it has this homological interpretation. I recall that we know from minimal resolutions we can calculate something like this and something like this from m to k, because if you have minimal resolution, home to k also vanish all differentials, and these things is just isomorphic to more or less minimal I tensor k and home from minimal I to k. Here is the opposite direction. It's from k to m. It's something different. In general, we can say something from minimal resolution for this. Okay. Now let's check this. In fact, the most not obvious part we have already proved on the seminaries was lemma, and now we will obtain corollaries of this lemma. Okay, proof of this theorem. We also need, I think, another lemma, but it's already easy lemma. Something like this, that if we have that x1 xk is a regular sequence in M, then k x kx isomorphic to home from A to M modulo x. Proof of lemma. Induction on K. no, base is kind of if k is 0, then it's the same thing. It's obvious. Induction step. What if I have a regular sequence? Then, because I know that it does not depend on order, the last one, from definition, the last one is not zero divisor in the quotient. But because it does not depend on order, I can consider the sequence something like this. And so, this is also regular. So by definition, this is also not zero divisor. I know that they all are not zero divisors. So for example, the last one is also not zero divisor. And I can consider the following short order sequence then. Multiplication by xk, m modulo xk. Consider the corresponding long sequence of x from k to this short sequence. No, yes, and easy observation, easy exercise. No, if you have multiplication by some element of the ring, then if you consider x, no, the corresponding map in x, it's all true for any ring. What is it? What do you think? Well, it's also multiplication by the same element because it's A modules. In our situation, for example, when A is commutative. And then, but in this situation, this map is 0. This map is 0. No, it's because, in fact, it's kind of home from K. If you consider some resolution, if home from K, then you can apply home from K and then multiply by some element of element. But or other hand, you can consider multiplication by this element in K and then home. But multiplication of elements in positive degree in K is 0, and so it's 0. No, if you do not believe, you can consider home for x0, for example, yes, and obtain that this is the same thing. It's easy observation. So, in fact, in long arc sequence, I have a short arc sequences because some of my maps are zeros. Okay. What kind of short arc sequences I obtain? I obtain something like this. No, I consider the leftist one, xk minus 1 a k m, xk minus 1 is induced by quotient. Then connecting homomorphism. And this is the end. But here I have induction, because here I have I have this regular sequence in M. So by induction, I have that this thing is isomorphic to home. Home from K to M modulo xk, modulo x1 xk minus 1. I need one proposition. It's a reformulation of lemma which we proved on seminar. So let me formulate it now. On seminar, we proved the following thing: if for any element from A plus there exists element from your module such that AM is 0, so any positive degree element is some zero divisor in your M, is zero divisor. Then it's equivalent to say that in fact there exists some common element M such that for any element from A plus, so there exists some common element M such that all A plus lies in annihilator of this element. But what does it mean? This means that What does this mean? What maybe I can reformulate the last row. No, this means that it's equivalent to say that A plus consists of 0 divisors of M. This one, what's such element? It's element which is annihilates by the whole A plus. No, I say that, and no, of course not 0. What this element? Such elements is exactly the home from K to A, because home over A from K to M, no, it's defined by the image of unit, and image of unit is exactly some elements which annihilates by any A plus, because unit annihilates by any A plus in K. So such elements in bijection with this home. So in fact, this is equivalent to say that this home is not 0. Okay? So in fact, from our seminar, we use that if A plus consists of 0 divisors of M, then this home is not 0. Because this home is exactly consists of such common annihilators. Okay? It's important observation. It's not obvious, but we have proved this. And now, okay, in this case, in this model, we have non-zero divisor. It's like xk. It's not 0 divisors in this module. So in this situation, this is not true. A does not consist of 0 divisors. We have xk. So this is 0. So this is 0. It's the main step. It's equivalent to say that contrary. So A plus does not consist only of 0 divisors, even though if this home is 0, because it's equivalence. There exists not 0 divisor of M in A plus, if and only if home over K to M is 0. It's a strong enough statement, but it's true. So, okay, we have not 0 divisors here, so it's 0. So this is 0. So we have this isomorphism. And this is by induction step. In this module, we have again this regular sequence, and by induction, this is already isomorphic to home from K to quotient of this by x1, xk minus 1. No, this is quotient of all our sequence. And this is what I want. Induction step is finished. No, this is the main ingredient of this proof, of course. This not obvious observation. No, we have proved this.
The first equation with x to k minus
this one.
Minus 1 is this, yes.
This also by induction.
But induction we make by
Length of regular sequence.
yes.
No, in this model I have regular sequence x1, xk minus 1. It's for previous regular sequence. x1, xk minus 1. This sequence is regular in M and is regular in the quotient also. So I have 2 induction steps. But here, from induction step and from our lemma, it's just 0. So in fact, we have no this thing, and we have only this thing. And by induction, I have. Okay. Okay. And now from this, I think it's more or less. It's more or less one stroke. Yes, one string of proof. Now let's prove theorem. Yes. Rees theorem, yes. Proof of theorem. Now let's assume that x1, xn maximal regular sequence. Now then it falls from lemma, because from lemma we know that x n k m is isomorphic to Hom. And maximality of regular sequence means that there is no zero, no, all elements are zero divisors in the quotient. And by observation, this means that this Hom is zero. Ah, sorry, not zero. Because we have no non-zero divisors here. If I have no non-zero divisors, that all my elements are zero divisors, then Hom is non-zero. So we obtain that for any maximal regular sequence, length of this, length of any maximal regular sequence, maybe they vary, but all of them yes, what I defined depth. Depth was minimal, yes, it was minimal I. No, yes, because minimal I means that I have 0, 0, 0, 0, and minimal I when it's not 0, yes? No, this means that if I know that n is non-zero, then minimal not greater than this number, yes? So we obtain that length of maximal yes, minimal I touch the text. Okay, we have checked this thing, okay? No, and oppositely. No, oppositely is also from lemma, yes. But if I have... ну yes, я тут себе это и написал, зачем-то я сейчас еще раз сделал. Вот, значит, but if... okay, consider such minimal I, what, denoted by n. So I have zeros before n, and n is the first non-zero, minimal non-zero. Now then, if n, if I less than n, so all my x are 0. No, this means that if I have some regular sequence of length I, yes, and then by this lemma, the corresponding x is Hom, x is 0. So Hom is 0. And Hom is 0 means that there exists non-zero divisor in the quotient. So this regular sequence is not maximal. In the quotient I have non-zero divisor, which can I add to my regular sequence. Okay? It means that Hom from k to quotient 0. This means that there exists xi plus 1 not zero divisor in this quotient. And this is equivalent to say that I can extend my regular sequence in one step. So it's not maximal. And I can do this before, since I obtain n. I think this is the end of the proof. So in fact, the length of all maximal things. This is the end or not the end? No, yes, and if I obtain, so any regular sequence can be obtained, can be extended to n length regular sequence. But n length cannot be extended by the same argument, because in this situation, my x is my Hom is not 0, so it cannot be extended. We have no zero divisors. So in fact, we obtain that any regular sequence can be extended to n regular sequence and not more. So all maximal regular sequence has the same length, and this is exactly the first number where x is not 0. No, because from this lemma we obtain, from this lemma and from this observation we obtain that this x is more or less abstractions for extension of regular sequences. And so we can extend exactly for the first non-zero abstraction. Okay, it's the Rees theorem. Now, the second and the final theorem about this thing is Buchsbaum-Auslander theorem. It relates projective dimension and depth. Theorem of Auslander-Buchsbaum. In our assumption, A is graded, commutative, connective, M is graded, non-negative graded, M is not 0, and I also assume that projective dimension of M is finite. Then I have equality. Projective dimension of M plus depth of M, it's over A. Its projective dimension, its depth of A over itself. Okay. First case, when depth of A itself is 0. Depth, yes, maybe what does it mean? Depth is 0. No, depth is minimal I where x is non-zero. This means that home from K to A is non-zero, and home from K to A is non-zero. It means that, no, it's more or less means that A plus is all 0 divisors in A. So it means that A plus are all 0 divisors, yes. 0 divisors in A. Okay. Maybe it's not important now. This okay. Maybe it's important to say that home from K to A is not 0. Okay. No. Anyway, consider minimal resolution of our M. No, because we know that projective dimension can be calculated by minimal resolution. It's natural to consider this thing. It's minimal resolution over A. N, K is exactly a projective dimension of M. But now, yes, in fact, what we need to check, if it's 0, we need to check that all two numbers are 0 because they are not negative, yes? So in fact, we need to check that projective dimension is 0 and depth is also 0. No, depth, in fact, no depth, let me check this is an exercise that no, if maybe no, okay, sorry. Yes, because if we check that projective dimension is 0, this means that M is free module, and then it's obvious that depth of M itself is also 0 because it means that home from K to A is not 0, and then from K to any free module is also not 0, and from K to M is not 0 too. So we need to check that in fact that projective dimension is 0, that all differentials. No, okay. So now consider.
So we want to prove that M is projective module, yes?
Free module, yes, because we know that overgraded thing, projective, flat, and free is the same thing. I need to check that all these things are 0 except of the last one, yes. Overgraded ring, projective, flatness, and free is the same thing. Okay. We checked this previous time. It was because all of these things equivalent to say that Tor from M to K is 0, because this can be calculated from minimal resolution. If it's flat, then it's 0, but then in minimal resolutions, all higher things are 0. No, or maybe the first one, because this is first thing. If it's 0, then in fact you have the first one, and so we obtain it's isomorphism with the 0 one, with the 0 term. If it's free module. Okay, so no, yes, we have such tensor product with k. It's differential. We know that it's 0 in higher terms, except of the last one. Here I have fk minimal itself, differential. And now, because I know that there exists non-zero map, no inclusion, non-zero inclusion from k to a, I can consider it. I have non-zero map from k to I, from to a. No, and it's easy to see that no. It's easy to no, it's not so easy. It's okay, such map. Okay, here I can consider, and I want to consider here identity tensor I. No, where here I identify tensor with A with model itself. No, yes, then this square is commutative. And I want to say just that this map is injective. No, it's because this map is injective, and these models are free, so they are flat. So tensor product with them preserve injectiveness.
This solves tensor product by A, yes?
Over A.
Over A.
And this is, yes, it's with A over A, yes, yes. And these maps are injectives because I is injective, and these models are flat, no, are free, so they are flat. So no, and then no, what we obtain that we have no, we have zero injection in something. What does it mean? Что сейчас засомневался на самом деле. Сейчас. Sorry. Yes. Yes. What here k is not is consider the last one. No, start with the last one. Yes. Here k is the projective dimension. The k is the last number, and then this map is injection also. Yes. But then it's 0. No, and then so on. Blah, 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 blah. If it's this 0, then we obtain the last one, and so on. And then all differentials will be 0, no, except this surjective. So we obtain that all things are 0 except of this one. And we obtain that M is free. M is free. Projective dimension is 0. And also depth is 0, because if we know that we have non-zero map from K to A, then also we, of course, have non-zero map to free modules. And so this home is non-zero for M, and so this depth of M is also 0. So we check this case, zero depth case. Okay. Now some induction. No, some case and some induction, yes. What case is remaining? When depth is greater than 0, yes. Then we have also one exceptional case. One exceptional case is when depth of M is 0. When depth of M is 0, так, ой, что это такое? No, then I just consider the following thing. Consider the start of minimal resolution. No, maybe it's not important minimal, just free, some projective resolution of free resolution for simplicity. Free surjective from free module, surjection from free module, and its kernel. Its kernel. Then, in fact, from long exact sequence in Next, from these modules, and from our homological interpretation of depth, you can check. Then from this and from Rees theorem, you obtain the depth of K what is it? For projective dimension, it will be -1 for projective dimension m. But projective dimension is the maximal non-zero. Depth is minimal non-zero. So in fact, in this situation, it will be depth plus 1. So for example, if you have multiplication by some non-zero divisor, you obtain something like this. And it's obvious that the depth, no, the maximal length of regular sequence here is 1 greater than in this one. It is the same thing. This plus 1. F is free model, yes. No, and it's important here that depth is greater than 0. So in fact, home from K to A is 0. It's important here for this. Okay. Yes, sorry. No, it's important here that it's 0. It's not 0, and then in fact, yes. Sorry. Of course, it's not true in general. It's true only if depth here is 0. No, from the start of long regular sequence, you obtain that if here home is 0, here home is non-zero, then you obtain x non-zero here. So it's in fact 1 what here. In this assumption, yes. Sorry, it's only in this assumption. No, because you don't know how many non-zero x for free model you have, because maybe if you have non-zero depth, you have some non-zero x for free model. Maybe it cannot to determine this depth, but in this situation, if it's 0, it's not 0, you obtain that this is 1. But of course, what is also true, that projective dimension of K is projective dimension of M minus 1. So, if we know this formula for any module of depth non-zero, then we know this for model K, and we obtain that formula for model M. So if we know that this thing is depth A minus depth M, and depth M is 1, so you obtain где тут что? Да, ну вот минус 1. Сейчас, что? Нет, все, получается все, что нужно, правильно? Depth AM, yes, it is 0, and you obtain equality. Projective dimension and depth. So what I want to say is that it's enough to check for models of non-zero depth, okay? Because if you have a model of 0 depth, you can consider this kernel, and if you know this formula for the kernel, you obtain this formula for your model itself, okay? So because, yes, it's equal to 1, and you obtain depth is equal to projective dimension. It's our formula because in assumption that depth is 0. If you know this formula for K. So it's enough we can assume that depth non-zero. It's not induction, it's kind of opposite argument. If we know for all positive, then it falls for 0. Okay. No, maybe not for all positive, for depth 1. Okay, so let's assume that depth M is positive and depth of A is positive. Okay, now the essential part. Now here it's also almost obvious. The only one thing is the following exercise. If you have two modules of positive depth, in our situation is A and M. What does it mean? This means that depth is positive. It means that for M and for N, there exist non-zero divisors for M and for N. No, I mean that there exist common non-zero divisors. There exists X non-zero divisor for M and N at the same time. No, it's the argument in the same manner. Maybe it's formal sequencing from this lemma of our symmetry, something like this. It's the same thing. I think even it's formal sequencing. Okay, now let's consider some X for A and M in our situation. X is non-zero divisor for A and M. no, then no, I have I can consider the quotient by x. Depth of A modulo x is of course depth of A minus 1. No, it's obvious by if you have maximal length here, you can add 1 again, and vice versa. Okay. And from the first exercise today, we know that quotient by regular sequence, for example, quotient by non-zero divisors, preserve exactness. This means that projective dimension of M modulo x over A modulo x is the same thing as projective dimension M. In fact, I think we have proved this as an exercise. It was the last exercise on the seminar. Yes, I think we proved this. If it's not divisor in M and X, we proved this. It was when step was obvious and base was Nakayama lemma. Yes, it's exactly this thing. It was today on seminar also. So, no, in fact, it's also it follows from exercise also. Okay, so what we obtain that what we obtain. No, we obtain that we have new ring A modulo x graded ring. So if we use induction on depth of A of our ring, if we use induction on depth, we proved for zero depth. And now if we use induction on depth of our ring, then our step to A modulo x, we can use this induction assumption. So we obtain that projective dimension M modulo x over A modulo x is the same thing as depth A modulo x minus depth M modulo x. No, yes, and here is also exactly depth M minus 1, and this is depth A minus 1. No, it is, and this is projective dimension of M itself. And this is finished. But here, the last remark. Okay, and so we proved. No, modulo this exercise. It's easy exercise. We proved by induction on depth. What the I don't know, hidden stone here. What the why in fact we maybe no. I say no. Then we prove this for finite depths. Yes. No, maybe you can. No, here I assume that projective dimension is finite. No, because it was important. Because if you remember, we consider some argument started from the last term of minimal resolutions. I need that this last term exists. It's important here. Yes. When we consider fk and this differential was injective and so I start from the finish of minimal resolution. So this is a place where it's important that projective dimension was finite. And in fact, you can think it's exercise. What if here is infinite? For example, you can see the exactly one place in the proof where the argument doesn't work, because I start my steps from the end of minimal resolutions. So I need the end exists. But I don't say the depth of my elements finite. So maybe it's finite. No, it's finite. But maybe so my formula say that this depth is infinite if and only if this depth is infinite. But in fact, in our assumptions, depth is finite. Maybe I will not prove this, but I just say that in our situation, no, вообще in general, it what you said before. As I said before, that depth of algebra is not greater than dimension of this algebra, crude dimension. no, in fact, this is more or less, no, if you think about this, it's not very hard because it's by induction. It's by induction. If you consider, you need to check that if you consider some non-zero divisor, and consider quotient by non-zero divisor, then we know by definition it's easy to see that depth is exactly depth minus 1, but you also can check that dimension is also exactly 1 lower. So dimension, cruel dimension is also dimension minus 1. And so if you have some maximal regular sequence, you can consider quotient and no, and then maybe by if you consider this quotient, then depth of this quotient is 0, and this depth is not greater than dimension of I minus n. So you obtain that n not greater than dimension.